So today I'm going to do two parts. So first of all, I'm going to go through some of the system functions that are built into Python. So basically some parts of the runtime library that comes along Python. So Python consists of the language interpreter, but also a set of libraries that are built in. So these are not external libraries, these are the libraries that comes with the Python interpreter. And one of the first things that is very useful when you do your scripting with Python at least is to be able to access the environment variables in your system. And if you have coded a bit, you know there is an environment variable called path with all the search paths for your system, but there could be other environment variables as well, controlling different aspects of your executable environment. And in Python, you can access the system environment using the OS module, which is kind of a high-level module for operating system functions. And in that module, there is a dictionary called Environ. And that dictionary contains all the system environment variables available to your code. And we can check it here by just printing out the path variable here. That will show you the contents of the path variable in your system. It's also possible to loop over these. So you can do, just with a dictionary, you can do for variable in OS environment. Then you can query each variable in itself here. So a variable and then OS environment variable here. You can also create your own. So inside your environment, if you want to call other scripts, for example, you can create environment variables that are visible to external scripts, not only Python script, but other scripts as well. And it's just like using a dictionary here. You just assign it the key here, that is the environment variable name, and then the value of that environment variable. And we can just validate here as well. So if I run this code here, you can see here, the first one here, I get the system path here. So as I'm running in the Google Cloud, we are running on a Linux machine, so you can see this is a Linux system path. On Windows, you will get the Windows system path, which is a bit different syntax, but it's still the same. And then you can see here, I loop over all the environment variables in the system, and you can see here, we have a lot of them here. So here you can see there are, because there are a GPU card connected to this machine, there are some other NVIDIA variables here. You can get the host name of the machine, language, current directory, environment, bash, a lot of things that are in the system you can get access to in Python. So if we go, so here you can see also that I have here my own environment variable here as well, which I printed out. So you can have both your own and your query the existing ones. So that is a good function to kind of be able to take advantage of the environment that the system provides. If you want to access the path in a more non-platform agnostic way, you can do that using a function called os.getExecPath. So that will instead present you with a list, or you can, it's a list of all the paths that are in the system. So you saw in the first part that you have this Unix convention of the system path. But for example, on Windows, you have a different way of using semicolons between the paths. So using this here, you get a neutral version of that. So if I run this here, you can see here, I get the path here. Of course, you get the Unix search path here, but you don't have the separators. So you get a neutral list of all the paths that are available. So here you can see that the first path it's search is the opt bin. And then it goes down like this. Another thing that can be important in code is changing your working directory. So in a Unix machine, you do, even in Windows, you do cd and the directory. You can do this as well using commands in Python. And the nice thing with using the built-in functions in Python is that they are platform independent. So you can run them on Windows, you can run them on Linux, it works the same. If you do system calls, you will kind of have to do if Windows do this, if Linux do that. And by using this, you get a neutral way of doing it. So The first thing is we can query the current working directory, and you can use the get cvd command to do that. That will return to the current working directory, and we can assign it a variable here if we want. We can change to upper level directory here by using change_dir ... This is the same as in when you do on the command line, but you don't give it a command cd. And then you can see here that would change, and then we can change back again. So see here, by default in the notebook here you are in the content. If you do ... you will be in the root, and then we can change back again here using the variable that we had before we stored here. That's also a command that is good to have, so that you don't have to do os.system, for example, to call the system command to do this. It's also possible to list files in a directory without using ls. Hello. Then you can do, there is a command called list_dir, and that will give you a list of all the directories in your folder. Or actually, no, so not only it will list directories and files in your current folder. And then you can loop over them here. You can also check if an item is a directory using the os.path.isdir function. That will return true if it's a directory. If it's a file, you can check it with isFile. So here you can see here a listed directory here. It just displays the directory contents like this. And then you print here .config, that is a directory. Test file is a file, and the sample data is a directory as well. So there's kind of a tool chest of good commands to have when you're working with, for example, automating your workflow. You want to move between directory, so you can check if there is a file there. Yeah, and you can also, here is a more elaborate example here of, you can also check if something exists using the os path exists command. And it returns true if there is a directory or a file specified by the search path here. So in this case, you can check, oh, is there a directory? If there is no directory os5, I will create a directory. And then I can go into that directory, and I can create another directory, open a test file in that directory. I can list the files. I can also rename files by using the os rename function. Remove empty directories, and you can remove files here. So this is just a large example of doing a lot of things at the same time here. So if we look what we did here, you can see here we created this directory here, and we also deleted the files inside, so it's empty here. You can also query information on the files themselves by using the scan_dir function, and then you can loop over the items in this return what it returns here. So here you can get each entry has a name, path, and also if it's a directory or is it a file. So you can get the path, the complete path of the file. You can also see if it's a directory or not. I don't commonly use that as much as list_dir and other commands. Yeah.
This as it.
Yeah.
I mean, to me, it implies some kind of iterator, but then I'm confused.
No, it's I can think you can do.
Is it just a list or what?
Yeah, items. Yes. So it returns a list of. Yeah, it would be a list.
All right, makes more sense. Then.
Yeah. Now I fixed as well.
Thanks.
Yeah. You can also do walk the directory tree as well. And then you use the os.walk. And for example, if you give it a dot, it will start walking in your current directory. and loop down recursively down the tree. And you get back here root, directories, and files. And you can use them to kind of, it will continue walking here. You can see that you have here config os sample data test file, and then it goes into config, and you can see it goes into the logs and the GCE directory, and it walks the entire tree of your directory. So if you want to search for things, you can use this to kind of go down the tree and find things. There is also querying file information. Here is actually something that I'm wondering. So the stat function is available on Unix platforms like Linux and Mac. You need to do something else on other platforms here, but it's similar on Windows as well. But what you do here, you do OS stat and the file, and then you get a lot of information, detailed information from the file system about that file. Same thing with the directory here. So if I run this, you can see here that you get inode information, you get links to the files when they are created, start modification time, creation time, and so on. Very detailed information here. And it's no, it's an object with methods to it. So I think you can type like this. I'll skip that last one here. Okay, now it complains because it already exists here. Let's skip that for a moment and just run it again. So you have attributes here on this object that you can query. So it's an object of type stat result that is returned back, and that contains all these extra attributes here. Path information. So usually one thing you do a lot in scientific computing is you manipulate paths in different ways. So what you can do here is you can use the path submodule in OS to get the absolute path. For example, if you give it a dot, it will expand that path to the full path. The base name is this one here, and then dir name is the first part here. So let's see if we run this. Let's see here. So you can get the base name is the text, the file, and then you can get the directory name here. And as I said before, the text you can use the exist to test if a file exists. You can also expand user. So if you have a home directory, you can use the tilde here to get the full home directory by putting that in, and that will expand to the user home directory. There's also a way, instead of querying the stat, you can do get a time, which is this modification time, and let's see here, this is a creation time and access time. And those are working on all platforms. So this is not only for Unix, it's also for Windows. The stat function is only for Unix. You can get the file size using path get size. You can also ask if it's if a path is an absolute path or not. Like this here, this is a full path on Windows, and it will return, if it should be return absolute path, and this should be no absolute path. Here you have isFile and isD. We already covered this before. So another thing that is problematic when you're working with both Windows and Linux is actually joining paths. Because on Windows you need to have backslash, on Linux you have /. And if you want to join paths, it's not, you can do it manually, and you have to check if I'm on Windows I should join them in this way, otherwise I should join them a different way. But actually, there is a command called join, which actually does this for you. So if you have a directory and a file name, the join can put them together with the correct path, or separator. So then you can make your code really non-system dependent. There's also the split function here that can split the path. On Windows, you can also split the drive, so you can get the drive, and you can get an extension of your file. So if you look here, you can get here split, you get the directory and the file name, and then you get the drive here. Not sure why I did that. Here you have the extension here instead. I'm not sure if I can check that, but .txt, so get the extension here. And all these you can use, for example, if you do split here, you can do dir name equals comma file name equals the OS path, like this. So you have OS path split, and then you can assign them. Then you have the directory name and file name in a single command. Of course, in Python you can do things in multiple ways. So there's of course another module that makes it even more simple to handle paths. I don't go too detailed on it, but the idea here is that instead of using strings to combine the path separators, you have a special operator. So if you create a path using the pathlib path class here in your current working directory, you can add things using the slash operator, and it will combine the paths automatically for you. So you get the correct one depending on the path you have. So in this case here, you see here that it will combine together here and by the slashes. So this is a special operator that is defined on this class here to be able to handle paths nicely between the different platforms. And you can also separate out the different parts of a path here using the resolve command. And there is also, if you define a path, you can do current working directory. You can also ask the object, do you exist? If it's a directory, it's a file. There is also a method that gives you the home directory. So path.home gives you /root here. So it's an object-oriented way of manipulating search paths in Python.
No, I was a bit confused about the first output. I mean, starting from the first lines of code.
Yeah.
That should start assigning p the value content slash, right? Because that's the path to here.
Yeah, well, what does it mean?
Print
p. Okay, test.
Because that exists should be the false value. Or am I missing this?
Yeah, I'm a bit confused now myself. So test is the first line here.
It should be, right?
Yeah. And this one, and then we do exists is false because I haven't created a file called test. But I think there is a test file.
So it will try to add this to p, but it will fail.
Print q. Okay, so this, then you do this and it will create a full file name here.
Yeah.
And this is the parts.
So the slash operator, what does it do?
Yeah. Let's see if I do like this instead of slash.
Right.
Okay, so because I think it was because the dot, it didn't do anything. But now you have the test. It adds test file to this, and when you print it, it gets the separator correct there as well. And on Windows, it would be backslashes.
Right.
Yeah.
But, okay.
And Q parts is this one here. And the drive, there is no drive in this, that's empty.
Because now line 3 is sort of system dependent, right?
Yes.
The forward slash.
Yeah.
So it would be nice to have that dot convention that you had, but it didn't work as I thought.
No. Then an interesting thing that will work on Windows as well, because Windows, if you're using the C notation, it will handle forward slashes as well, because it's, yeah.
Huh.
Yeah.
I need to look into that path.
I'm not going too deep in this, as I said, but it's there and it's object oriented, and you can combine different text files and directories using the slash operator instead. And then you can also iterate using this here. So if you have a path here, you can use an iterator here and loop over recursively here as well. So this iterdir function here, it will iterate over directories.
And now it somewhat points towards the right, starting directly with the dot.
Yeah. So it starts in the current content directory, yeah, and then goes through that.
It clearly understands it to some degree.
Yeah. It's just that if it's dot, it will perhaps be represented in the shortest form, and then it's the test file is without the dot. Yeah, it's. I have to read the documentation for that. You can also change the path using. So you can put changed here, and it will return you something that you can use in the normal commands as well. Right. And you can use .cvd to print out the current working directory as well. So you see that you change here, and then the current directory has changed, and that will return as a path object. Yeah, the same example as we did before. More importantly, something that you will probably use is temporary files. And there are ways of doing temporary files. You can, of course, do them yourself. If you are running your code in a current directory, it's possible to just create a file that is temporary. But if you want to create a temporary file using the mechanisms of the operating system, which you can do, and also if you want to do it more securely, there is a module called temp_file that can create temporary files for you, which are created in the correct location where you should have temporary files in your operating system. So if you just run this, I can show you here. So now you can see it created a temporary file in the temp directory here, which is the correct placement in a Linux machine. And then you can use this as a normal file. And then finally you have to erase it as well. So this make as temp will not remove the file automatically. That is something you have to do yourself. But it will create a temporary file with a unique file name. So you can't guess what the file is. You can also use the temporary file class to create a temp file object. And that will automatically remove the file when you don't need it anymore, or when you have used it. So in this case here, I get this as a normal file object. Then I can query it, and I can write to it, I can seek to it, and then we check here what happens afterwards here. So if I run this, there is no file anymore. So it's gone. So this one will create a temporary file. You can use it during this code block. After the code block, the file is automatically erased. Let's see here. Another thing that is something often done in Python is that you control your scientific workflow in different ways. And that usually involves starting applications in your Python script, waiting for the return, continuing execution, doing something else. There are many ways of doing this. The simplest form is actually what I haven't shown here, but os.system. So if you type os.system, you will execute a command. The code will block and continue after os system command. So I will see if I can just add one here. So you can do, for example, os.system list files. And now it didn't put any output here because it just executes the command and just returns. So the 0 here is actually the completion variable. So result, the command completed OK. If you want to have more control, there is a special module called subprocess that can run commands in different ways. So in this case here, you can do subprocess run, and then you have ls minus and the commands like this. So this doesn't start any. It calls the operating system directly without a shell. So this is the binary, and this is the command line to this binary, and then it executes that one. So then the result here contains the return code 0. So it's very similar to our system, but this is the simplest form of calling it. Then you can do more. So perhaps you want to have the output of your code. You can add some parameters here, stood out, which is standard output. You can tell it that I want to have a standard output process and want to get that back. This is a special thing that you need to have. I'm not completely sure why you need it, but this is to process the output correctly. Then if you run it here, you will have, in the result variable, there is a standard output attribute now, which contains the output of the code. So now you can see here it returns 0, and this is the output from my executed code. So now you can process that in Python for what you want to do. It's a string. Then another thing, if you want to execute something but you don't want to stop at this position and wait, you can actually use something called popen, process open, and that will execute ls and that binary, but it will return directly, and you will get you get a process handle or process object that you can use to interact with the process. So P here is the object that monitors the process that has started, and then you can do other processing. The code continues, but then if you want to kind of make sure that the sub-process has finished, you can use wait, and it will wait until the code has finished at that point. But here you can start doing other things, and then at some point you just check. So it works just like the code before, and you can see here it returns 0 here.
Without that wait command,
it will just continue here and finish. Without the wait command, this is a bit problematic Python code, because especially if you're running in a script, because when the script ends, you don't have any way of checking what the output would be if the code finished or not, because it will continue. It will just start the code, continue here, and terminate the Python code, which also terminates the open command here, because this belongs to the Python process.
Yeah, but P has been assigned something.
Yeah.
And then if we skip the wait command, we want to check things in P.
Then you will probably, we can see what happens here. I think it's a bit too quick to actually test it. Yeah, then you don't get any return code.
So it hasn't been assigned a value yet, but it's there.
Yeah, so you can do that for start something that is long running, do some processing in Python, and then at some point you need to wait for the other process to complete. You can do p.wait, and then it will wait until that is finished.
That's just interesting, because I guess P would be filling up with, for example, the output. Right?
Yeah.
And you can sort of process that output while the process is running, right?
Yes.
I guess.
Yes, you can.
Live check.
Yeah.
How many lines have been printed, or how many words occurrences up to this point, or whatever. Right? So, I mean, P is still a useful object.
Yeah. Then you have to handle the pipe in a certain way to read from that pipe as a file.
Okay. Yeah.
When the wait finishes, it comes through the code as an interruption, or we need to check and validate what is the state of the waiting?
The wait will block here. The code will stay there until this process has finished. And this process could finish with an error. It still needs to kind of wait for that to complete, and then you can check the return code.
So we cannot go to another instruction while waiting.
No, wait is kind of blocks. But you can do like the next example here. So if you don't want to wait blocking, you perhaps want to check continuously, is it still running? Is it still running? You can use the poll command. So while poll is none, it kind of then it's not finished yet, and then you can kind of wait here until this process completes. So I have sleep 5 here, and you will see that it kind of waits until the code like this. So in this way you can start it up, but that you don't have to block. You can continue to check that it's completed. And then here you get the return code as well. It's also possible to, so the previous commands here actually execute the process without any shell. So it just takes the binary and executes that with an argument. You can also execute it within a shell context. So here you put a variable shell true that will allocate a shell for you that it's executing in. And then you also have standard out, standard error that you can also do. So when you have done polling here, you can communicate with the code using the pcommunicate command. That will also return the standard output and the standard error to this. And that you can do during the process as well. So standard output is empty because the ls command didn't do any errors. But the standard output is the directory listing, and the standard error is empty here. And then also one thing with you actually need to do is you should actually close the process when you're done. So in this case here you can use the with like we did with files. You open them and then make sure that the process is closed at the end. It's just the same thing here. And also pcommunicate will kind of wait until you get all the data before it continues as well. So it's kind of blocking in that sense. What do we do here? So what I usually do to kind of make my code a bit more readable is I create a command like this, execute with output, and then I have my command line here, and then I do subprocess here and do all my processing and just return standard output or none. When I execute. So in this case I can just do execute with output ls, and if output is not none I just process the output, and then you can have multiple of these without having a lot of code. So you can see here that I get the output here from ls, and I can process them. I split the output here, and then I add lines to my lines list, and then I loop over that. So this way you can execute some kind of computational code, you can process the output from the code, and continue using that in Python as well later on. So this is a way of kind of executing code, creating a workflow in Python that you control. So also, when you are, probably when you're debugging your Python code, you're familiar with using print to kind of show what is happening during your code. There is a problem with print, is that it's not always prints out directly. So a lot of the things in code is buffered somehow. If you really want to make sure that you always get log messages when it happens, you can use logging. And there is a logging module in Python which you can use. And then you can do, you can tag messages here. So logging debug, that's a message that you only see when debugging. And then you can set a filter on this to only show certain things depending on what level you set. So here I have set the level to error. That means that only error messages will be printed here. So the warnings, the info, and everything is not printed. Also the critical, because critical is higher than error, so critical message will also be printed. If I change this to debug, you can see I get all the messages here. And you can also have info. And you get info, warning, and error as well. These can also be, you can create your own logging, you can do logging in any function you want to do this. You can create your own logger, and you can set the level here on your special log, and you can change the level here as well.
That was sort of what I was missing in the previous example.
Yeah.
Thinking about objects in the one above.
Yeah.
Because there is no clear object to me here that is sort of.
No, there is so logging is a module.
Yes.
And there are actually functions in that module that you can call directly.
Yep.
So what I do is you could have from logging import star. Then you could just do debug info warning.
Oh, yeah, right.
So these are not. So logging is not an object. It's a module that has a method that you can do call.
And you can set the level for the entire sort of.
Yeah. So this is the. This gets the default logger object, and then you set the level on that default logger that is built into. So that is kind of there is a single default object that can then handle logging by default, but then you can also create your own loggers, and then use those for debugging instead.
That seems more familiar to me at least.
Yeah. And then you can do, this is something I haven't got to work inside a notebook here, but it's also possible to create configure the output of the logger in a different way. So you can put the format here to kind of display date and time and warning levels and stuff like that in your own format. And of some reason here, this works if you run it on a script, but not in a notebook. So I'm not sure why it doesn't change here. But it should have been the date here and the name. But the date is missing here for some reason. I'm not sure why. But basically, you use the basic config command here to configure the logging output. So if you have large applications that you want to use it to be able to fine-tune the output, use a logger. For small application, print is fine. I mean, it works as well. But I think if it gets larger and you want to be able to other users to configure it, it could be a good idea to use the logging functions. Perhaps not in a notebook is probably not so necessary. But if you have a standalone Python application, it could be a good idea to use logging.
And you said that the empty get logger method there would return sort of the default logger or whatever.
Yes.
And then I can sort of store that to, well, my own variable if I like, right?
Yeah.
And I would like to set a name just to make it distinguishable from other things.
Yeah. And you can also you can set these to go to files as well. So you can log to files instead of logging to standard output. So by default, it logs to standard output currently. But it's by setting different options here, you can also control where the output should go. But I'm not going too deep. There is a lot of documentation on this that you can use. This I don't know what it is. It shouldn't be there. Then the other parts that is really nice in the runtime library is the ability to structurally store things in files in different ways. So we already talked about files, writing to files, reading from files, but you can also write to your more complicated data structure to be stored in a way that you can read them back and get without any complicated parsing of your file. And there is a module, there's a file format called JSON, which is JavaScript object notation. And it's very similar to the Python data structures that you have, like dictionary or lists. So if you open a JSON file, it actually looks like a Python structure. So for example, here I have a dictionary here with some values in it and lists and different things. I have done import JSON here to get access to this. It's built in, so you don't have to install it or anything. It's built into Python. You open a file, here as my file here, and then you do JSON dump. My data, you give it your file object and your data, my file here. Sorry, right way around. You dump your data to my file. And then you can open it back again. And then you can see here you do open for read my file. And then you do JSON load my file. And it returns you a new object here with the data inside the object. And we can see here how it looks. So you can see here that my data copy here is a dictionary again. So I can write my dictionary with all the data just down to disk, and I can read it back again. And you can see here if I cat the data here, this is the file on disk. It kind of looks very similar to a Python object. So JavaScript has decided to use the Python notation for its data structures. So you can create a file format for your input files that is a JSON file and just load it like this. Not very complicated to write, and also it can have really complicated structures, and you can just read it in with a single line. You can also do it, you can dump to a string. So in this case I have my data here, I do dump my data and it returns you a string. So in this case I get a string representation of my object in my code, and I cannot go back again here. I can take my string and go back to data here again, which is here. And this could be used if you want to send data over the network. You can do get a string and send that over the network. Now you can receive the data, recreate the structure again like a Python dictionary. You can also, if you want it a bit nicely formatted, you can also set some extra parameters here. So you can do sort keys indent 4, and then the output will look something like this instead. Which is kind of, if you have a user input file, this is perhaps a better way to kind of write your input file. So JSON is highly recommended. It's perhaps not for huge files, but for input files or for data files, it's a very nice format to both read and write. And imagine you're doing that file format yourself using just text files. You read a text file and you have to parse the text file yourself to recreate this. The JSON modules does this for you. There's another format that is a bit more efficient if you want to store things, and that is the pickle format. And pickle is actually older than JSON. It's something that has been with Python since the early beginning. You can see the similarities here. You have my data here again, and I open a file. There is no specific extension for pickle files there, so I just put pkl here just to put something. They are binary. That's why you have to do double B for binary when you write them. But you use dump just like we did with JSON. You open it again, read binary as my file. And then you pick a load again. Works just like before. And if you look at the file here, there should be what I do, my data.
Going to step one up.
Oh.
I'm not sure you're still in.
Okay, here. Yeah, we changed the directories too many times here. You see here, you can't read because it's binary.
Does it save space? Or?
Yeah, it's a bit, so if you have more larger data structures, Pickle is to prefer. But I would say also that if you're using NumPy, there are built-in functions in NumPy that is even more efficient. So this is for the standard data types in Python, the Pickle, this built-in module. But NumPy, I would look at the methods that are in the NumPy array object to store files. We will look at that later as well. Also, some notes here about there are different. So Pickle has evolved during the year. So you always write in the latest format, but you can also dump in older formats. And there is a protocol here that controls the version of the Pickle protocol. And I would say that consider Pickle files to be temporary files. I would not use them as your file format for input files. Then it's better to use JSON. So Pickle can be used to kind of quickly dump something, quickly get it back. Checkpointing for your applications, for example, could be you can Pickle down and then Pickle it back. Same thing, you can of course do this to strings. Then you can see here that when I print my data dump here, it's a binary string. Contains no things. But I can take that binary data stream and then do that as a load, and then I get my data back again. So that is a nice way of using as well. Also, and here there is also ways of using tar files. So tar files is tape archive that I probably heard of it. This is a way of like zip files in Windows. It's a way of archiving a set of files in a single file here. So I just downloaded some images here, and there is a tar file module called tar file, and I've imported as TF, so it's a bit shorter. I can instantiate a tar file object just like a file. In this case, I open it with, and I get the my tar back here, and I can just add 2 files to it. That will create the tar.gc file. I can do same thing here. I can when I open existing one, I can query the names inside the tar archive. I can extract files. I can extract everything. I can list the files with verbose true. So let's see what happens here. So you can see here the get names. I will get the 2 file names that are in the tape archive. I can also get members here. There are more detailed information in each of these tar info objects. I can also get information here, list the files in the archive with more attributes here, like the file sizes and the file names and the date, creation date, and so on. And you can see here I get the my archive.gc here as well. And there is a zip files module as well. So you can actually handle zip files as well directly in Python. For some reason, the syntax is different. I don't know why, but it should have been the same, but it's not. But you do zip file, this module here, and then I just use ZF to make it easier to use. You do ZF zip file, and then I do open it, and then I can write files to it. So instead of add, I use write in this case. I can open it. I have to create, I can do a name list here, get info, extract all, print directory, and so on. So it's similar, but not completely. So here I managed to open the file here and show it in Matplotlib. So you don't have to search and use external commands for zip files and tar files. That is built into the runtime library of Python. Yeah, and you can also combine this together. So if you want to have a compressed pickle, you can use the clib library. So I have my data here. I dump this to a string. So I get my data dump here, that is a string. I print out the length of the string here just to kind of see that something happens when I use it. I do clib compress my data dump. I get a compressed data stream. I check the length of this. And then we go the other way around here. We do decompress on the compressed data stream. And then I pickle it back again. So you also have a compression library here. So you can see here I go from 2811 to 1915 bytes. And then I go back again using decompress. So that is also built into the runtime library Python. So there is a kind of mantra of Python that batteries are included, and that's kind of correct. There is a lot of things in the library. So before kind of searching for things, external libraries, check the runtime library of Python. There is a reference on the Python homepage with all the modules that are available in Python. I'm not sure what I want to do here.
But these JSON files, they can be used on other programs.
Yes.
But Pickle probably not.
Pickle is only Python. But the tar files can be used on a zip file as well. And the JSON files that is a JavaScript standardized notation. So, and you can see a lot of programs that use JSON files for configuration files and other things. So it's a kind of useful text file format that is structured. And a nice thing with this is that you can very easily add things to your file format. And your old program can still read it, even if you add more things to it. And that is problematic when you do your own file formats. Then you have to have versioning information and different read methods. But with JSON, you can have you can have compatibility backwards, unless you remove things.
So if I would use a Python script to create some data, and then afterwards use it in the Fortran code, then I should write it to JSON and later open the Fortran.
The problem is that Fortran can't read JSON. Then you have to have a JSON library that reads the JSON file in Python in Fortran. Okay. But that could be done.
Okay.
It's more like
so it's not so easy.
It's not so easy. Because Fortran's runtime library is smaller.
Okay. They don't know JSON.
No. I'm not sure if they will do either. So it's but it would be nice if Fortran's string manipulation and stuff like that would be more.
Because currently I write very complicated, the right position, the new line.
But what you can do is probably create binary files from NumPy that you can read in Fortran. So that is probably the best way to go to Fortran if you want to read files. You only have to make sure that the binary format is correctly defined. But it's doable. JSON is probably much more complex.
But JSON would be nice.
Yeah.
But if it's not read, then.
But check it, because there is in Fortran now there is a package manager, and there's a lot of new packages being made available. So I wouldn't be surprised if there is a JSON reader. So that could be worth checking. But JSON is not for creating huge files. It's more for creating moderately sized things. Especially if we have dictionaries and stuff like that in it. Okay. I'm not sure why I did this one here. My data range 1000. I will add a comment to that. Other formats that are available is there is also common configuration file type called ini files. They were introduced with Windows at some point really long time ago. But they are files that are where you can have different sections denoted by brackets. And then you have variables, names and values like this. So you can have variables sorted in different sections. And there is a module that you can read called a config parser that parses the config files. So this you read, and then you can get the sections. You can access it as like a dictionary here. So Bitbucket user will go into get this information here. And you can loop over them in different ways. I've started to use more and more JSON for my configuration instead, because this JSON gives you more structure. This is kind of just section variables. So we can see here, we can parse this one here. And you can see here it prints out the information inside the config file. You can also write config files in the other way around here. So comma separate files is also available built in. Very rudimentary, I would say. I think Pandas is more, if you do large data structure processing, Pandas is more suitable. But you can do some simple things here using the CSV reader, CSV writer. But it's almost like CSV files you can do almost by yourself. I mean, it's just strings separated by commas or semicolons, so it's not that complicated. And also I would say that if you have larger files that have structure, reading them in Pandas gives you more benefits. We have a Pandas course as well, so keep a lookout on the web pages. So that's about my first part. We can 10 minutes break, and then I will start with more object-oriented fun. So the next part here, I will look at object orientation. And as I said before, object orientation, you already used it when we work with strings. We used split, for example, which is a method on the string object. And usually, when we talk about object orientation and programming, objects describe nouns such as point, circle, equation, model, square. Objects usually also interact by sending messages. And the messages are the verbs that you want to perform on the object. And the message in Python is actually a function. So we don't send messages, we call functions on the objects. And an object consists of methods, the verbs, which define what you can do with the object, and properties that describe the attributes and links to other objects. And objects are designed using classes, so the class is actually a blueprint of an object. So the class in itself is not an object, it's just a description of how objects are designed, or how they should look. But first a bit about function-based programming. So up until now we have used a lot of, we can define functions, we can define data structures, and if you have a program that can only do functions, you can still achieve a lot of the, you can solve the same problems, but you have to express it in different ways. So here I have a library here which can create a point. And this could be a more complicated data structure than just a list of X and Y. But it creates a point and returns this list here as our data structure. We can move the point, and the point here, all the functions have a point as the first argument here. So we modify the point, we can zero the point, we can set the point. So you define a complicated data structure for your, it could be a planet, it could be a particle, or a molecule, or anything, and we can modify it here. So it's a really simple function library. And we can use it here to create a point. So in this case, we give it 2 coordinates here, and we get the point back here. And if we print point, we pass this structure along, and we have a function that can print it out. So of course now it's very simple data structure, but it could be more complicated. But the idea is that we have a data structure we pass along to have functions operate on it. And this is what you do in C, for example, if you want to do object orientation, is that you define a structure and you have functions that operate on that structure. But the function themselves doesn't know about, so the data and the functions are separate. And this is what we have here. So we always have to pass the P along to work on it. We can set the point here and it will update the P data structure. With object-oriented programming, you kind of turn this concept around. So you combine functions and data in a single object. So the class describes what attributes you want to be able to your object to have. It could be mass, it could be position, it could be velocity or anything. And you have methods here that operate on that object. It could be move, it could be set, it could be anything that you want the object to be able to do. And the object the actual object that you want to work with is created from the blueprint. So you have the class and you create a new object and say, I want to use this object should be of this type or class, and it creates that object. So for example, if I have a class that is called planet, it has a lot of attributes, the mass, the radius, and so on, and I want to create 2 planets. I create 2 objects here. So what I do when I create a new object is I give the name. And we have already done it today when we created the path, for example, path objects. We did path parentheses. That created an object of the class path. So in here I create an object of the class planet. And the convention is that you give the class name and the parentheses here. And in the parentheses, it could be that you provide additional parameters. And that is passed to something called a constructor. I will go into that, but it will be used to initialize the object. So I have 2 objects now, Mars and Jupiter, which both are planet of the class planet. They have their own attribute variables, different from each other, so they are copies. So if you change a variable in Mars, it will not affect Jupiter. So they're self-contained. And in Python, you create classes by using the class keyword. And you can see here that the same kind of structure as we have with functions. You define class, point, colon. Then there is a code block. And the first thing we have to define in an object is actually a way of initializing the object itself, which attribute it should have. And that is done using a special function with the name init. Init is called at object creation. So when we did here, this is where the object is created. And that calls this function here for the planet, of course, and now it's a point here. And here we initialize x and y to 0. So now the point has, when you create the point, it by default has the position x 0 and y 0. It could be other objects for the planet, could be mass and radius and so on. I have a special class here called point with ID, and that is just to illustrate the concept later on here. You can see there is a self variable here. And that self variable is the reference to the actual object itself. Because this is the only way for a class to be able to reference the actual object itself. So when you create an object, self will be the memory location of the created object. So it comes in here, and then self here, you assign those to this memory location. So that's why we have self. So self refers to the actual object that's been created.
And it must be included there in the init.
Yes.
Is this function referenced as the constructor in Python as well, or is that word used in other languages?
Init is only in Python. What do I know? I
mean, just this special thing that creates objects. It's in C family.
Yes.
But it's the constructor.
So in C++, you have a constructor. That is there's a function named as the class itself. In Python, they have decided that the constructor is called init for classes. But the concept of constructors and destructors are available in all object-oriented languages. Right.
Could I call the self also eigen?
No, you have to call it self.
If I call right there eigen, could I then continue with eigen?
No, it's a special word. So it will probably complain. Let's see here.
No, but then I have to write eigen x and eigen y in the next.
Now you're putting.
Well, I'm just wondering, is that?
Let's see if it works. If I do just put e here.
I guess the init function handles its argument quite special.
Let's see if I do. It did work. Let's see if I do the same thing with this one here.
So the question is this a convention or is it a Python?
Seems to be a convention, but the first argument passed is the reference to itself.
Okay.
So I need to check that. I have never tried. I've always learned to put self there because it
makes sense. But
yeah.
It's just
that.
This alludes to this function of the init function.
The underscore init is a reserved word, yes. A reserved function.
Yeah, that's clear.
But the question if itself is actually something that you need or
is it from the namespace? So, for example, if you would use self for something else, for whatever reasons.
Yeah, you can see it. I mean, it indicates that it's kind of a reserved word. So I'm surprised that it actually worked. But it could be that this will be the first parameter. That it still works. Because you get a reference for the object and then you use E here instead, and then it's the same thing. It refers to the same. The only thing is that you never call it, you don't have to call it directly with the self parameter. It's hidden. But I need to check if you can actually have any word there, any variable.
And then, of course, you can have any word. Why should I have any word?
Yeah, you can. Yeah.
So, I fully agree, but there may be a reason that you want to have the self as a variable.
It could be a convention, but I'm not 100% sure. But what you can see here, at least, is when you create two objects, they are different in memory. So they are its own instances. And if you run this here, you can see also that P and Q, now they are initialized to 0 because we put that in the constructor. You can change the variables here, and then they are different. So they are unique, each of them. One of the things that you want to achieve in Objective is something called encapsulation, that you want to hide the internal workings of your objects. And what we did just here is actually not encapsulation, because we can access these attribute variables directly. So if you want to do this, real encapsulation, hide the internal workings and just communicate with methods to our objects, because it could be that X and Y are stored in a database somewhere. They're not variables, but you still want to have an object that can handle easily. In Python, there is no real concept of private and public. So by default, everything in a Python object is public, but there are ways of actually hiding things. So if you add 2 underscores to a member variable or attribute, you can't access it from outside. So in this case here, I create a point here, but I put X and Y as underscore here. This one works, of course, but if we want to try this here, you can see here that point objects has no attribute X. So now we have hidden X inside here, and you can't even do like this, print p.x. That also doesn't work. So let's see if we can just comment these out here. So using this, it's not even possible to access this variable from outside here. So this is a way we can hide things, internal things in Python. Let's put it away here. Yeah, as I said, this doesn't work either. So to be object, and then we have to, all variables inside an object should be accessed using methods and functions, or methods to get that. And the one way of doing this is, you see this in other languages that you can do, you have getters and setters. So you have a special method that sets the value here, and one, in this case, we just set the value here, and then we set the value internally here. And then you can set it like this as well, with X and Y. Now we can use the same notation here, but then we can have p set to set the position and x to set the X and Y. Of course, we need to, now we can just set them. But if we want to get access to them, we have to be a bit more careful. We change here to that X returns the value, and we have a set X to set the value. And now the class is a bit more complicated again. We have to set and set X, Y. But the benefits of this is that you can, as I said, you can store the X and Y coordinates somewhere else in a different data structure. The user only has to care about the interface of the object. Other things is hidden inside. But the nice thing with Python is that you can actually achieve the same thing using something called Python properties. So properties is something that I heard it first actually in Object Pascal. It's a way of faking attribute variables, but making them as easy to use as having an attribute variable that you can access directly. So the idea is that you define your getX, setX functions like this, and then you add this here to your object. So you say that X equals to a property, you read the X value using the get function, and you set it by using the set function. And now, all of a sudden you can, if I redefine this one, you can actually use it as the first version of the object we created. So if you do like this, you can see here that if you do X equals to 42, it calls set X. If you call Y here, it calls set Y. So the assignment actually goes and calls the method with that parameter. And if you print it, it will get X and print it out, get Y. So why do we need these kind of things? And one reason with properties is that you can implement, you can check the ranges. For example, if you assign an X that you don't allow it to be negative, you can, in the set, you can handle that and set it to 0, for example. You can do things during the assignment with your variables. So you can control the value. For example, if you set here, you can see a set Y value greater than 42, it keeps it at 42. So if we do, now you can see here already here, if we set it to 84, didn't allow it to be greater than 42, and it set it to 42. So you can internally handle these cases directly. But another benefit is that you can start small when you start implementing classes. You start with the declarations we did here in the beginning, the really simple things. This. You start declaring just normal attributes to your class. And if you need to control a certain variable, you can add a property. And then you can have the same control as having functions, get and set functions. So to prototype and start up, you can use this, and then you can add the encapsulation later on without affecting people using the code. But there is an even easier way to do properties, and that is using something called decorators. And decorators in Python is a kind of meta programming term. So you, for example, here you add property, this add property before your X function here, and that will define X as a read property. and I do @x_setter, that will define x to be also have a property that you can assign. So you don't have to define these extra property declarations below. You just add these decorators to your functions, and you get automatically properties.
Sorry, did you find something x 2 times?
Yes, but I have two versions of it. So I have, this is for returning the value. It is a function just with, so see it as an empty. This itself is never, you don't never call that, and it returns the value of x. And this x function here sets the value. Perhaps it should be value instead. Like this. So this sets the value of the internal attribute here. And then so this is only for assignment. This is for reading, to getting the value out from the object.
When you say that some attributes are public, that means that any other user in the same Python environment can access that information, or it's on the same console?
So a public attribute is when you have a Python object where you have defined your attribute in the constructor without the underscores. Then x is, you can the p object you can access x directly on the p object. That is public. If you have double underscore, Python will restrict you so you can't get access to that internal attribute. So that is hidden. But there is no real private in Python, because you can get the dictionary of the object, and then you can find the underscore x anyway. So it's more of a, the convention is that if you have double underscore, Python will prevent you from accessing it.
But if I'm having another Python console from the same environment, can I get can I read these attributes from the dictionary?
Yes, so you have these global objects in Python, and every object you create is a dictionary as well. So if you're willing, you can go into every object and query them. It's possible in C and C++ as well, but then you have to do memory manipulation. So in Python, everything is a dictionary, basically. And so you can, if you want to, actually modify objects anyway. And it's also actually possible during runtime to add methods to objects as well. So Python opens up a really lot of interesting ways of programming. Because if you have a class, you can actually add methods to the class afterwards. And you can replace functions in a class as well. So, but it's also open up for nobody understanding what is your coding. Because if you start doing dynamic modification of your code, it's difficult to know what happens. But there are some, for example, web development kit that actually you pass some function an object, and it returns you the object again, but with added functions to it. So there are ways of using that in a nice way as well, but it's not something I go through in this course. Yeah. But the thing is that if you want a property like this, this is the thing you have to define, a way of reading the attribute. The setter is optional. So this is a way of, you can have attributes that are read-only. You can only read them, you can't assign them. So you can see that if you do px, it calls the setter for x. And the same thing here, it calls the property of x here. So it works the same way, but you don't have to collect all your properties at the end and define the x equals the property, you will get the set. You do that directly by putting these decorators on top of the methods. Yeah, now we have gone for the properties. properties, but then you have also instance methods. And those are actually what you want to do with the object. So in this case here, for example, it's not much complicated than using normal functions in Python. You have move here, for example. All the methods in an object has to have the first parameter as self, but then the other ones here are optional parameters that you can call the method with. So in this case, I define a move here, so you can do point, punct, move, and then it will move the object delta x and delta y. So here you can see here that I create my points, and then I have an instance method here that is used to kind of interact with my object. You can see here that it's moved the objects and the x and y positions were updated. You can also, where a common method is also copy from. So I have another object and I want to, not to copy the object itself, but the values inside the object. So I can do, then I give it another point reference here, and then I assign my own internal attributes to the points x and y values. So in this case here, I do P1 copy from P0, and you can see here that they are the same. So P1 is the same as, did I print? Copy from P0. Yeah, so it's 1020 here as well.
Just to get that. So that you would use if you have two planets, Mars and Jupiter.
Yeah.
And then you want to transfer a property from Mars to Jupiter.
Yes.
And then you write copy from Jupiter, comma, Mars.
Yeah, so if I want, yeah. So if you have you have a lot of attributes that you want to copy over in a controlled way, you write a function like that to transfer them over to the other object. Because if you do the equal signs here, you have a problem again, because that is if you do Mars equals to Jupiter, that is then Mars refers to Jupiter.
Yeah.
So the copy from is good to kind of get a copy of it. Then there are some other special instance methods as well, which are kind of useful, or very useful. So what happens if I print an object? I've defined my own object and I print it, it looks like this. This is not so nice to look at. What you can do is you can add a special method to your class that prints it in a nice way. And that method is called __str___. So you can see that all these special methods have underscores before and after.
Oh, that's also reserved.
They're reserved, yes. So what string here, this function expects from you is that you return a string representing your object. Now usually you do a representation that basically is the constructor again, but in a nicely printed format. So here I do print point, and then I put x and y coordinates here. So let's define that. And now you can see here that if I do the same thing here, it prints out my point in a nice format. And you should, if you have your own object, you should have, I think it's important that you have a nice way of printing out your objects, especially if you're looping around different object types and you want to kind of see what the actual object is, then having a nice print is a good thing. And also remember, you don't print here, you return a string, and that is printed by the print statement here.
So it's not advised to write a print function.
Just if you want to debug your str function, but it's the idea is you return a string, and that is then processed by Python. That is a convention.
So this is when you have this, you put into the class.
Yeah. Your own classes.
Into your own class, you have the class planet.
Yeah.
And there you write this.
Yeah.
And there you say that if I print planet, then there comes mass is equal, distance from sun is equal, visible, yes.
Yes. Could be.
Which are variables you have defined as belong to the class. Exactly.
And that becomes important then when you have lists that contains different object types.
Yeah.
If you want to print them out, they should kind of display themselves as their actual object.
Mm-hmm.
So classes as data types. Your own classes can go, they are identical to every other object in Python. So if you have a list, you can put as many points as you want in a list. You just create them here directly and add them to the list. And now if you, it didn't print it out here, but you can also do, this is a short form of that. I can do this, I do the list first for p in points, print p. So now you can see here that it's, because we have defined a print statement, we can print them out, and you can see here that, okay, this is a point, and it has a position x and y here. You can make the output even more rich if you want to. It's nothing that prevents you to do that.
And what would this behave reasonably if we print the points list directly?
That will be...
What would the output look like? It's a list of planets.
Let's see. We haven't done planets. So you can...
No, points, sorry.
So in this case, it contains references to this. It doesn't resolve that.
Right.
You can, of course, this is a tip here you can do. If you want to create a list without doing a for statement, you can do stuff like this. You can do what's called list comprehension. So you can put a for loop inside a list here and it will create a list directly here inside. It's the same thing as the above here. And then you can print, here is the, okay. I will remove this here. Yeah, and also the variable references are the same here. So, of course, each object here, if you do p2 equals to p0, the reference is other here. So you can see here that p0 and p1 are these addresses, p2 and p3 are these addresses. So you can't, like I said, assign Mars equals to Jupiter, then Mars is Jupiter. So that's something to think about. Another thing that is also good to know about object orientation is inheritance. So what you can do is you can define new classes that derive functionality from existing class definitions. So for example, a circle, we can use that, we can derive from point, which has an x and y coordinate, and we can extend that to be a circle. So in this case, we have to add another constructor here. We use the same arguments here, x and y, but we add a third here, which is the radius. And before we initialize our circle, we need to initialize our inherited objects as well. So we need to pass along the x and y coordinate variables to our point initializer. We could have done this like this. But this means that you need to kind of write the actual derived class every time you do the constructor. So there's actually an easier way to do that. We can use super, which refers to the inherited object, and then we call init on that. So then we can have the same statement every time we create an object. You don't have to put point there as well. Because if you change the name of pointer at some point, you need to change this here as well. So with super, you don't have to do that. But this initialize calls the constructor or point, and then x and y is defined, and then we add r here, and then we add properties r and r setter. We add a copy from here because we need to modify copy from because it's now also have to handle a circle. We update string, otherwise if we print a circle, it will print point, so we update this one as well. Add a radius here. The nice thing here is now you can create points and you can create circles, and they inherit from each other. So for example, the move method is the same for both the circle and the point. Now circle also has a radius here, and if you print them out here, you see here that point prints out x and y, and circle prints out x, y, and radius. So that's the way of reusing code. And there is a current debate in how much inheritance you should use. I have tended, when I started coding in C++ many years ago, I tended to use a lot of inheritance. But I've learned since to kind of limit the amount of top-level classes and keep them, because it's not every time you can find a natural inheritance. So my tip is also, when you do object orientation, have a pen and paper, sketch the nouns of your programs, planets, stars, suns, and then, okay, can you find logical inheritance here? Otherwise, don't do it. Perhaps you have something common for all the certain objects or planets, and then you can have a base object for those. Composite classes is something that is more common today, that you kind of create new classes combining multiple classes together. So, for example, a line has no natural inheritance to a point, but it can consist of 2 points. So in this case, we create a new class here that has 2 attributes that are points instead. And then you can see I put line from to here. So here I can do line, and then I can access P0, which is my first point, the second point, and then I have access to the attributes of point 0 and point y as well. Well, point 0 and point 1, x and y attributes. And then it's interesting what happens here. You see I have defined 2 properties, P0 and P1. But there is no setters. So if I run this, I get an error here. I can't set attributes P0. And it's because we only have defined 2 read-only properties. So P0 and P1 are protected from overwriting. You can read them, you can set the attributes, but you can't create your own instances and assign them to the points. We can change this by adding setters. This is a design decision you have to make when you design objects. You want the objects to be able to be reassigned, the instances of the points, or not. You have to design yourself. Here I have the redefined line to add setters of P0 here. So now I can set the internal points. Now this will work here. So you can see here P0, P1, you can assign new points to the P3 and P4 and assign them here. And now that's perfectly fine. But it could be that there, for some reason, you want the point to manage its own objects. And you don't want the user to be able to overwrite them. Then you only provide the property decorators, but not the setters. You can see here that you can actually design your objects to be resilient for user manipulation. You can kind of protect your objects in a way that you couldn't using normal attributes. And we can add a property here to calculate the length of the line. And here is a typical property that doesn't have a setter. So in this case here, I just add a property length here, normal function here for calculating the length of the line. And now I can use the property length here, just like a normal attribute variable, but you can only read it because how do you assign a line a length here when you have defined your points? Then there's another concept of object orientation called polymorphism. And that means that if you have a number of objects that have the same methods defined to them, Python makes sure, or the language makes sure that you call the correct method depending on the object type. And also, if the method is not available in the current instance class, it goes one level up. So for example, if a circle doesn't have a move object, it will go up to the point and look, oh, there's a move method, and it calls that one. And that means that you can have mix of instances, different type, and it ensures that you always call the correct method during the when you call this here. So in this case, to illustrate this, I create a shapes list here, and I add my objects to my list here. And you can see I add a floating point here as well. I add an integer and a string. And I call print shape. And this is an example of object polymorphism. So you know that there is an str object method on all of these classes. Python figures out here, okay, point, then I need to call the print method of a point. I have a circle here, it calls the print method of circle. And if circle wouldn't have a print method, or this str method, it will go up and use the point version of str. Of course, it will print the point there as well, but it will find it. But what happens here? 42. It also works. Because if you look here, everything in Python is an object. So there is actually a str method on the 42 object, the 42 floating point variable. Works perfectly well. So everything you define, even a floating point value, an integer, is an object that has the str method. Then it's implemented more efficiently with 42 because it has an efficient way of handling floating point. But if you call this, it works. So this actually works for all the objects in this here. So you can see here that the list can contain any kind of object, and Python knows how to handle this. And also it could be that, for example, you have a set of objects that you only have defined, and you have a certain method of moving or updating. For example, if you have a certain kind of molecule, it has an update method that does something special. Another molecule has another update method. And you can loop over and call update on all the objects in the list in the same way, and it finds the right method to call automatically. That is polymorphism. And now we have the lecture is over. I don't have so much more here, but you can see here, this is what I meant here. So I have 2 points in circle, and I can call move, shape, move. So shape here, I don't need to know what the actual type is. I can just call move here, and it will know how to move itself. Because point and circle have a move method. So on Thursday I will do a more graphical example of this and how you can use it. No planets involved, but circles and shapes moving. Yeah. So that was it for today.